From the cruise control in your car to these massive industrial plants that run 24/7, our world is just built on incredibly complex automated systems. They operate with this amazing precision, often with almost no human help. But have you ever stopped and wondered who the unseen architects are? The ones who actually teach these machines how to think? Well, today, we're going to find out.
It's a pretty cool question, right? And the answer leads us to this crucial yet often invisible role, the controls engineer. They're the ones designing the logic, building the brains behind the automated world we all depend on every single day.
Okay, so think of a controls engineer as the ultimate problem solver for any system that's in motion. Their whole mission is to bring stability to processes that are always changing, to make sure everything just runs like clockwork, safely and efficiently. Really, they are the true architects of automation.
So, every automated system, it starts as an idea, right? A blueprint. This first phase is all about design. It's where these abstract concepts get transformed into a detailed, concrete plan. This is where the foundation for everything, and I mean everything, that follows is laid down. And this isn't some random, chaotic process. It's a super structured journey. You start with concept formulation. That's the big idea. Then you get real specific with requirements, defining exactly what this system has to do. From there, you move into basic and then detailed design, where engineers create these incredibly intricate technical blueprints, planning out every single component and connection before a single thing gets built.
Now, what's really interesting here is the honesty. Let's be real, this initial design phase can be messy. You're exploring all these ideas, and most of them are probably going to get tossed out. But, as this quote from a real-world engineer points out, it's also where you have the most power to shape the final product. It's confusing, but it's also incredibly exciting.
And that's why, at this stage, the design engineer is truly the project's architect. They're not just drawing lines on a screen. No way. They're making the fundamental calls that will define how the system behaves, what its safety features are, and how reliable it'll be for years to come, all before a single wire's even connected.
And this is their digital toolkit. You've got AutoCAD for the detailed drawings, sure. But the real complexity is managed in specialized databases, like SPI, which can track thousands and thousands of individual data points. And what's absolutely crucial is software like MATLAB and Simulink. That's where they run powerful simulations to test how the system will behave in the virtual world before it ever gets built in the real one. And of course, everything they design has to strictly follow international engineering standards for safety and compatibility, no exception.
All right, so we're leaving the office and heading out to the field. This is commissioning, the high-stakes stage where that digital blueprint finally becomes a physical, functioning reality. This is where it gets real. If you had to boil down this entire commissioning phase to just one word, this would be it: integrate. It's the process of making hundreds, maybe thousands of individual components, sensors, valves, motors, controllers, all work together as one cohesive, intelligent system.
Now, during this phase, roles get pretty specialized. You might have a programmer who's just laser-focused on a single PLC. That's a programmable logic controller, the brain of one machine. But the controls integrator, they've got a much bigger, more holistic view. They're responsible for making the entire system work, troubleshooting everything from a bad wire to a network glitch to make sure all those different pieces are talking to each other perfectly.
And you gotta understand, this phase is intense. As one engineer on Reddit put it, the hours can be absolutely grueling. Commissioning is done under immense pressure to get a plant or a facility online, and the work just doesn't stop until the job is done. It's a really methodical, almost painstaking process. You start with basic inspections. Then you do what are called loop checks to verify every single signal path, all the way from the sensor out in the field to the screen in the control room. It's only after all that that you can finally conduct functional tests to make sure the logic actually works the way you designed it to.
Okay, so the system is up and running. Job's done, right? Not even close. Now the focus shifts to the long operational life of the asset. The engineer now becomes its guardian, responsible for its long-term health and safety. And this phase is all about precision. This checklist here is for a big plant-wide distributed control system, or DCS, basically the nerve center of the whole operation. And look at the details. They're checking controller temperatures every single day, making sure critical backup systems can switch over in less than 50 times milliseconds, and testing cable insulation every month. This relentless discipline is what keeps a multi-million-dollar facility running 24/7. But it's not just about the checklists. There's a really deep satisfaction in this work.
As engineer John Braithwaite puts it, there's this unique euphoria you get from solving a complex puzzle, from hunting down that one root cause, and knowing that you just made the entire plant safer and more reliable. That's a huge deal.
But here's the thing. This role is evolving. Fast. The old way of doing maintenance was about fixing things after they break. The future? Well, the future is all about using data to prevent failures from ever even happening. It's a massive leap forward.
And this is that future, predictive maintenance. Instead of just waiting around for a failure, this strategy uses constant streams of data and powerful analytics to forecast exactly when a component might fail. This lets engineers step in before a catastrophic breakdown, preventing all that unplanned downtime and saving, potentially, millions of dollars.
So what does it actually take to thrive in this field that's changing so quickly? Let's break down the essential toolkit for the controls engineer of today and tomorrow.
The modern skill set is a true hybrid. I mean, the core skills are still absolutely essential. You have to have deep knowledge of machine controllers like PLCs and those big plant-wide DCS systems. But now, skills in system integration and, you guessed it, data analytics are becoming just as critical. It's this blend of hands-on hardware, complex software, and cutting-edge data science.
And specialization is how you advance your career here. For engineers focused on safety, getting your Certified Functional Safety Engineer, or CFSC certification, is the absolute gold standard, especially in high-risk industries. And for those who are great at leading projects during that intense commissioning phase, the Project Management Professional, or PMP, is a direct path into leadership.
Now this right here might be the single biggest shift of all. That wall that used to exist between information technology, the world of servers and software, and operational technology, the world of machinery on the plant floor, that wall is gone. To work with predictive maintenance and secure all these connected systems, skills in programming languages like Python and a deep understanding of cybersecurity are no longer just nice to have, they're essential. When you really think about it, controls engineers are the ones solving the most fundamental problems of modern industry. They are the unseen architects, the integrators, and the guardians. So the real question isn't just who teaches a machine to think, but as this field keeps expanding, what incredible new challenges will they teach it to solve next?